Great. Welcome back, everyone, to MATA02, the magic of numbers. This is the very last week of lecture. So this is the last week, and then you'll have a couple weeks, and then there will be the final exam. And so today we're going to be talking about public key cryptography. So in the last week or week plus of this class, we've been talking about some of the actual applications of these things. I promised you wouldn't have any applications. In fact, for many of these things, when they were developed, they really didn't have any applications. A famous mathematician is reputed to have said that he was really glad that he worked on number theory because it had no possible applications. This was, of course, only a couple of decades before people invented cryptography. And so, unfortunately for him, it turned out that people managed to make the math useful, even though he didn't want it to be. So let's think about some mathematicians. They prefer their math to not be useful, but it's my job as an applied mathematician to force them to be useful, basically. Anyway, so what is public key cryptography? Well, let's go back to our usual story about communication. So, well, we have Alice, we have Bob. So these are the persons A and B. And then we also have a nefarious party, Eve, who is our eavesdropper. I keep on, so I probably will misspell this at some point, but eavesdropper actually has the A in there after the E. And I keep on messing it up because I keep on thinking Eve, the character. But anyway, so Alice and Bob want to communicate. So maybe Alice is talking to Bob, or maybe Bob's talking to Alice, or maybe both ways. But the issue is that Eve is overhearing all of this. And you want some way for Alice and Bob to communicate without Eve knowing everything they're saying. Oh, the people online cannot see the lecture slides. Okay. Yep, thank you for letting me start that again. Okay, can the people online see my lecture slides now? Let me go ahead and, okay, can everyone see that? Okay, and the people here can still see everything as well. Okay, great, sorry. Okay, but anyway, so in today's lecture, we're gonna be talking about public key cryptography. We have the usual communication story. So we have Alice and Bob talking to each other, and Eve is listening at the door trying to hear what the two of them are saying. Now, of course, if Alice and Bob are able to communicate a key in advance, then they can encrypt their conversation, so that even if Alice can see what's going on, unless Alice breaks the cipher, unless Eve breaks the cipher, she won't be able to know what they're saying. So we're going to put a lock on this. So we're going to put a lock on it, and that's basically the story of encryption, right? You want to keep some privacy by not revealing to people, to eavesdroppers, what you're saying to each other. But now there's a bit of an issue. So we covered a couple of oh wait, just a moment. Why did I not? Okay, something went weird with this file. But anyway, so I thought I deleted out that text. But anyway, so the basic idea is you have symmetric ciphers. So you're adding a number to every letter of mod 26. So in the Caesar shift, right? So that's what the activity we did on Wednesday. The number you add is the key, and if you know the key, you can both encrypt and decrypt. So for example, if I had the message yes over here, and what I wanted to do is I wanted to encrypt it with the key 2, which you can also think of as just B. So I have a key 2. That's basically the same as saying the key is the letter B. Well then, yes is 25, 5, and 19, YES, and you add 2 to each of these, you get 27, but that's of course just 1, 7, and 21. And when you map these back onto letters, you get AGU. So you can do that sort of encryption, but once you've done that encryption, the decryption uses the same key, right? So for the decryption, all you're doing is you're subtracting by 2. So you start with AGU, which is 1, 7, 21. You subtract 2 from everything, of course, in mod 26. So when you subtract 2 from 1, you get 25 in mod 26. And that gets you back the yes. And we also covered some other ciphers. So for example, we talked briefly about the Visionaire cipher, which adds a cyclically repeating word to a message mod 26. So you do the same kind of strategy you do with the Caesar cipher, except that you don't add the same thing to every position. Instead, you add a different thing to each of the positions. And so, for example, if you want to send a message to Toronto with the key CN, well, what you do is you take Toronto and then you repeat CN over and over again so that you have a letter for each spot, and you add them together according to the same addition rule as mod 26 that we were doing for the Caesar cipher. And decryption operates very similarly. So for the decryption here, what we're going to do is we're going to subtract CN, cyclically repeating. And so what you'll notice is, of course, that when you use a key, the same key that you use to encrypt is the key that you use to decrypt. And that's quite important, because what it means is that if you know how to send a message, you also know how to decrypt the message. Okay? Now, the issue here is, what happens if you have eavesdroppers? Come on. What happens if you have an eavesdropper? So what happens if Eve is really there listening at the door for the entire conversation? So like we said, the symmetric ciphers use the same key for encryption and decryption. So this only works, right, if Eve only hears part of the conversation. So this is all right if, for example, you're a Roman emperor and you're sending your generals out into the field and you want to have some way of communicating messages to them while they're out in the field. Because you can just, while you're all gathered around in your boardroom or war room or whatever, you can talk to each other and be like, oh, hey, I'm going to use this key for my messages to you. You just need to remember that particular key. But the issue is, of course, if you have a spy in the war room, well, then everything is completely revealed, right? So if Eve ever hears the key, then she can decrypt the entire conversation, both past and present. So because Eve remembers the conversation, has written it down, and so if she ever gets the key, then everything is lost. Okay, so what can we do about that? Well, how do we beat a perfect eavesdropper, someone who's listened to everything? What if Eve knows everything Alice and Bob have ever said to each other? So there's no way for them to share a secret key without Eve knowing. In fact, we'll go ahead and say that Alice and Bob have never even met, but they're just communicating on the internet. For example, let's say that I want to buy a particular sci-fi novel by Neil Stephenson. Let's say I want to buy the novel Cryptonomicon, which is a story about a person learning an encryption algorithm. Well, I mean, it has other stuff in there, but one of the central parts of the story is they actually developed a new encryption algorithm for this story using a deck of cards. If you're interested, look that up. But anyway, let's say that I want to go and buy a book online. And so I'm trying to buy the book Cryptonomicon, but in order to do that, I need to send my credit card information to the bookstore. But I've never met this book. Well, I mean, I have met this bookstore, but let's suppose that I've never met this bookstore and the bookstore's never met me. So we have no way of communicating except through the internet. But now if there's an eavesdropper listening in on my Wi-Fi connection, if there wasn't any encryption, or they had somehow managed to figure out the communication between me and the bookstore, well, then all of a sudden, there's no way for me to send them an encryption key that the eavesdropper doesn't also hear. So what can we? That is a very good point. So like many of you have seen sponsor messages about NordVPN, and yes, somehow it hides your traffic. But if you've never talked to NordVPN before, because presumably you'd be buying NordVPN from online, how do you initially share a secret with NordVPN? Presumably we have to give them your credit card information or something. I don't actually know these full sponsor messages for NordVPN. Probably heard of the many times, so I sort of tuned it out now. But anyway, so like if you were going to do that, how would you initially set up your communication? And that is where all the math that we've been learning in this course really comes into play. Okay, so something is horrendously wrong in all my writings on here already. So, but we'll keep on going. And if I start going too fast, please let me know. The reason I erase all my handwriting off of the slides whenever I'm presenting is because if I don't have to write it out, I start talking really quickly. So just FYI. But anyway, so the key here is with symmetric encryption, your encryption and decryption use the same key. What happens if they use different keys though? What happens if you have one key that encrypts and another key that decrypts? Or maybe if encryption doesn't need any key at all, but only decryption needs a key. So with symmetric encryption, that's sort of like having a lockbox, right? So you have a key, you put it in, anyone who has the key can open it up, put a message in, or take a message out. On the other hand, asymmetric encryption is a little bit more like having some of you might have these locked mailboxes. So what they are is they have a little slot for the mail to go in, but in order for mail to come out, you need a key to open it up. And so that's a little bit closer to what we would consider asymmetric encryption. So if you had something like this, then Bob could give everyone the encryption key, which we often call public key because, well, it is something that would be accessible to the public. You give it to everyone, so it's everyone knows it, but not tell anyone the decryption key. So that's the private key. So if Bob could do this, Bob could tell Alice the public key, and that's fine. And it's fine if Eve overhears the public key because that means that Eve will be able to encrypt. But if Bob just never tells anyone the private key, since it's private, then that means the decryption key, that means no one else can decrypt, even though Eve hears everything Bob has said to Alice. And that is basically the crux of public key encryption, is that there's some way, some magical way of coming up with does that mean Bob can receive messages, but Alice can't? Yes, that is exactly what it means. So that means that Bob can receive messages anyone sends to Bob, and only Bob can decrypt them. But of course, you could set it up so Alice can also set up a public key, so that way Alice and Bob can both send messages to each other. But yeah, so in the basic version that we have described, only Bob can receive messages. But then of course, once Bob can securely receive messages, Alice can send messages to Bob and then like, oh, hey, use this encryption key. And then you're done. Or you can have both Alice and Bob set up a public and private key. And then when they communicate with each other, they encrypt to each other's keys. We'll go into this in a little bit more detail. And with that, actually, I am actually going to give a 2-minute break because I do actually need to remove some of the text from this. So you can see me. So let me do that quickly. I'm going to delete. I don't know why this didn't update, but let me update this. And see what's going on. And then we'll keep on going from there. Oh, I'm just on the wrong version of the file. That makes sense. Okay. You'd think I know how to do all this by now, given that I've been doing this all semester. But, okay. Okay, so let's keep on going. So basically, the point is that this way you can send messages to each other using this public-private key system without, if you could do this, then you could send messages without the two parties have ever having talked to each other because you separated the idea of your secret key and this public key. And that's the whole point of asymmetric encryption, and this is the foundation for internet commerce. But how do we do this? Well, we use the magic of math, we use the magic of numbers. So what are the various things we've learned in class? So one of the very first things we learned was that somehow whenever you are defining operations like addition, multiplication, subtraction, division, well, going forward is often easy. Like addition, multiplication, powers, those are all just faster ways of counting. You just repeat some operation over and over again. On the other hand, subtraction, division, and roots, these are reversing the operations and they're harder. In ordinary numbers, often what that means is you have to invent new numbers to deal with what the result of a subtraction, division, or root is. In modular arithmetic, well, we've seen how much harder they are. This week's quiz is all about finding roots in modular arithmetic, and you guys should know at this point how much work that is. But somehow reversing things are harder. And another one of the problems that happens to be hard that we're going to talk about is specifically multiplication. So for example, if I multiply together 4931 times 7919, well, this is relatively easy. All of you have known how to do that since grade school, right? This ends up being 9048589. And you could do it just by doing long multiplication. You multiply each of the different spots, and you figure out, you add them together, and you get the answer. Multiplication is relatively easy. But on the other hand, well, we talked about how division is hard. But if division is hard, then that means that factoring is even harder. Factoring is hard, right? If you wanted to find the factors of this number, and I think I chose 2 different prime numbers to multiply together, well, you would have to check and divide by each of the numbers smaller than it going up to it. And so that means you'd have to check 4,000 some odd numbers before you get to the first divisor. In fact, as we said, in order to test if this is prime, so even testing if prime, even testing if prime accurately is hard. Because remember, you'd have to go up the square root of your number in order to accurately test if it's prime. So that's not quite true. There are some clever ways of going faster than that, but generally speaking, factoring big numbers is hard. And this is really important because we can multiply things together easily, but then breaking them back apart, that's hard. And yes, for small numbers that we've been working with this class, it's relatively easy, but for the big numbers that computers are using, it's much, much more difficult. And that is going to form the basis of public-private key cryptography, which is, it turns out there are some problems that are easy to go forward and really hard to go the other way. And this is the basis really of much of cryptography. Going forward is easy, but going backwards is hard. Because what this means is that when you're doing a particular problem, you can ensure that some other party doesn't have information that you've given them. If you give them the result of something going forward, going backwards is hard for that. Okay, so as I was saying, figuring out if a number is prime, just determining if it's prime is relatively easy using probabilistic primality testing, right? So this is something we covered in class. So basically, what you do is you check things like 2 to the 142 mod 143. That happens to be equal to, and yes, it takes a little bit of time to do this, but that happens to be equal to 114 mod 143. So 143 is not prime. So in order to show that something's not prime, all you have to do is find some number where if you try to apply Fermat's little theorem, it fails. On the other hand, factoring a composite number is hard for large numbers if you don't know any divisors. So 143 happens to be 11 times 13. But in order to factor that, you might need to test all primes up to the square root of 143, right? Because that's the only way you can ensure that you tested all the primes that could be one of the divisors. Okay, so now I'm hoping I've convinced you that there's this problem that's hard. Factoring is hard. Multiplying is easy, factoring is hard. But luckily, testing if something is probably prime is actually still relatively fast. And so this combination of things that are hard and easy is what's going to allow us to do public key encryption. So let's say that we're trying to find roots with Euler's algorithm. Well, I mean, we've done this many times. You all are going to be doing that in your quizzes this week. Let's go through a simple example of this. Let's say I want the third root of 7 mod 15. Well, you have to check a couple things. You have to check to see if the GCD of 7 and 15 is equal to 1. And then what you have to do is then you have to compute phi of 15 is equal to 8. So you have to compute that. And the only way to compute that is, maybe not the only way, but the easiest way to compute that is using the factoring, right? So if you know that 15 is 3 times 5, then you can compute phi of 15 is equal to 8. And then you check that GCD of 3 and 8 is equal to 1. And so this means that we can find a root using the methods we've learned in class. So what do we do? Well, we find 1 as a combination of k and phi of n. So let's do that. So 8 is equal to 3 times 2 plus 2. So 3 is equal to 2 times 1 plus 1. So that means 1 is equal to 3 minus 2. 1 is equal to 3 minus 8 minus 3 times 2. And then 1 is equal to 3 times 3 minus 8. 1 is equal to 9 minus 8. That makes sense. But then what that means is you can rewrite things. So that means that 1 plus 1 plus 8 is equal to 3 times 3. And one of these 3's here is the m. And then you can rewrite using Euler's theorem that the 7 to the 1 is then congruent to 7 to the 9. Because 7 to the 8 is congruent to 1 by Euler's theorem. And because this is all mod 15. Yeah. And then you just plug this in, and then the root is easy. So the third root of 7 is congruent to the third root of 7 to the 9, which is congruent to 7 to the 9 times 1/3, which is congruent to 7 cubed, which if you write this out is 49 times 7, which is congruent to 4 times 7, which is congruent to 28, which is congruent to 13 mod 15. Okay, so that means that if we can, we know how to use Euler's theorem to find roots. But what do we need in order to solve for roots? Well, let's go back to thinking about what's hard and what's easy. So reversing versus going forward and all that. So computing a to the k mod n. Well, what do you need? You need a, k, and n, right? Because all you're doing is you're multiplying over and over again. And yes, there are these clever methods you can do where you break it up into powers of 2 and all that. But regardless, the point is that you can compute it straightforwardly using just a, k, and n. And you know how to do that. So for example, 13 squared mod, 13 cubed. 13 cubed mod 15 is congruent to, well, I'm going to rewrite this slightly. I'm going to rewrite as minus 2 cubed, which is congruent to minus 8, which is congruent to 7 mod 15. Okay, so that was relatively straightforward. On the other hand, what did we need to do in order to compute the root? Say we wanted to compute the cube root of 7. Well, in order to do that, we needed a, k, and n, but then we also needed phi of n, right? So we needed an additional piece of information in order to compute the root in mod 15. Because in order to use Euler's theorem, we need to know what Euler's phi function, Euler's Todian function is. And this is congruent to 13 mod 15. But the method for this was the previous slide, and that was a lot more work, right? So it was a lot more work to compute the root, and you needed this additional piece of information. So this information is hard to get if factoring is hard. And we know factoring is hard. So this is hard because factoring is hard. Because factoring is hard. So in fact, if you don't know what the factorization of 15 is, then you can't find the root at all using the methods that we described, right? So this is really a crucial piece of information. And this forms the basis of the RSA algorithm. So this was Rivest-Shamir-Adleman in 1977. So this is really recent mathematics because it was only invented, well, I guess 50 some odd years ago. Wait, 50? No, not even 50 years ago, less than half a century ago. And this was the first public key crypto system, which allows two parties who've never communicated before to securely send messages to each other. So they don't know anything about each other except one party, Bob, publishes a public key and is like, hey, if you want to send messages to me to encrypt them so only I can read them, this is how. And this, of course, is what made internet shopping and banking possible, because you can communicate securely with other computers without worrying about eavesdroppers. And so this is one of the foundations of modern computer security. And I'm going to describe the full algorithm. It is kind of long. You all might have seen it if you were, I think I put that algorithm on your handout on last Wednesday. We will be going through this again on Wednesday. So this coming Wednesday, I will have another interactive where I'm going to have you all do an RSA example and send messages to each other. So just FYI. And I am emphasizing that I am trying to emphasize that you all should learn how to do these sorts of encryptions and decryptions. They may show up again. And given the time of the year, you can guess where they might show up again. Okay, anyway, what is the RSA algorithm? Well, the first thing that happens is, well, the two people have never met, so they have to introduce each other. So Alice introduces herself to Bob. So Alice says to Bob, hey, Bob, I want to send you a message. Or I want to send it to you in a way that no one else can read it because I don't want my messages being out there for everyone. So Alice introduces herself. Well, then Bob is like, well, that seems hard because we've never met each other. But luckily, I know lots of math. And so then what Bob does is Bob does this crazy thing. Bob generates two large prime numbers, P and Q, and computes the product, N is equal to PQ. Okay, well, why do you do that? Well, because then Bob generated two prime numbers because he knows how to do that using Fermat's primality test. But then he multiplies them together and you get this composite number N is equal to PQ. Now, in order to find what P and Q were originally from N, you'd have to factor N. Well, we just said that factoring N is hard. And so this means that Bob has a secret. Bob knows P and Q. but he can tell the world n, and the world doesn't know what p and q are. So this, yeah, so Bob chooses an x, so this here is the secret. This is the secret that only Bob knows. Bob then chooses another number, k, which whose greatest common divisor with phi of n is equal to 1. So because Bob knows the prime factorization of n, he also knows what phi of n is. So Bob chooses an exponent k, where the greatest common divisor of k and phi of n is equal to 1. And then Bob sends this pair, n and k, to Alice as a public key. In fact, he can publish it to the world. He can be like, hey world, if you want to send me messages, send them to this particular public key, n and k. Anyone who knows the public key can send messages that only Bob can decrypt. So anyone who has this information can send messages to Bob, but no one else can decrypt them. Well, how does Alice send a message? Oh yeah, so it's like this mailbox example. So how does Alice send a message? Well, Alice has a message A. Let's say that the message is a number. Obviously, we know how to encode letters into numbers, and so this means that you can send a text message by doing this. So she sends she has a message A, she wants to encrypt it. So what she does is she sends B is congruent to A to the K mod n to Bob. So as we said, figuring out roots in mod n arithmetic is really, really hard if you don't know phi of n. And Alice doesn't know phi of n, so she can't decrypt that message, but she can encrypt it, because encrypting it is just a matter of taking powers. Well, and then Bob can decrypt it though, because Bob knows how to compute roots in mod n arithmetic, whereas Alice doesn't. In fact, Bob is the only one in the world who knows how to compute roots in mod n arithmetic. That is the secret he has. He knows how to, he has the superpower. He can compute roots in mod n arithmetic. No one else in the world can, unless Bob reveals the secret. And this is the crux of public-private key cryptography and the RSA algorithm. Any questions there? This is a complicated algorithm. We'll be going through it a couple of times. And you'll notice that it makes use of all the different tools that we've been covering in class so far, from the factorization of prime numbers, power properties, roots in modular arithmetic, and so on. Okay, so no questions. Let's walk through this carefully. So let's say that Alice has a message. Let's say the message is A is equal to 42. So maybe Alice wants to say something about the meaning of life, the universe, and everything. Regardless, her message is 42. So Alice introduces herself to Bob, says hello there. And then Bob is like, okay, well, you want to communicate with me. Let me generate a public key so you can send me encrypted messages that only I can decrypt. So let's say Bob chooses P is equal to 4931 and Q is equal to 7919. So these happen to be two prime numbers. In practice, you would actually need something like hundreds or to thousands of digits in your prime number. This is, you need your prime numbers to be really big in order for the security to be good enough. But we talked about this earlier, right? When we talk about primality testing, you wanted numbers that were quite big, but you could still write down on the page if you had. So we have these quite big numbers. And how does Bob find these numbers? Well, he can find these by generating random numbers and using the Fermat primality test. Primality test. Right? Because if you pick a random number, if you pick enough random numbers, one of them is probably going to be prime. And then you can test if it's probably prime by using the Fermat's little theorem. There are other tests as well, but the basic idea is Bob can find two big primes. And then Bob multiplies them together. So then n is equal to 9048589. And factoring this number is hard. So if I just gave you this number, it'd actually be quite difficult for you to factor it by hand, because you would need to test every single number up to about square root of this, or every single prime up to 4931. So that's hard. But Bob knows n and knows the factorization. So then what Bob does is Bob chooses an exponent k with the greatest common divisor with lat n phi of n equal to 1. So how does he do this? Well, he knows that phi of n is equal to, well, it's n times 1 minus 1 over p times 1 minus 1 over q, right? Because that's the factorization of n. But then, of course, that's just equal to if you multiply this out, that's p minus 1 times q minus 1. So that turns out to be Euler's phi when you carry through with the formula for a product of 2 primes. So Bob knows what the phi of that number is, and then he chooses k is equal to let's say 23. Okay, so he chooses some exponent k. I hope I did that exponent right. I don't know if I remember to check if that GCD is actually equal to 1. But anyway, so he checks that exponent has the right GCD. And of course, we know how to check greatest common divisors, right? But you just use the Euclidean algorithm, and that gives you the greatest common divisor. So you can check these things by just doing division. So you check these things, and then you publish the public key. So public key will then be 9048589 and 23. And note that often you'd want your exponent to be bigger as well, because if the exponent's too small, you might be able to brute force it. But we're going to sort of sweep these technical details under the rug. So you have this public key. Well, and then Alice has a message she wants to send. So what does she do? Well, she sends the message B, which is equal to 42 to the 23 mod n. Okay? And she can do this just by knowing n. She doesn't need to know phi of n, because all you just do is multiply, and then you take mod n, and it gives you that answer. And then Bob can decrypt, because Bob knows what the 23rd root of B is. Because Bob knows phi of n, and no one else does. Excuse me. Okay, how's everyone doing? Okay, let's do it again, because so let's give another example. Alice wants to send the message 196 to Bob, but doesn't want eavesdroppers knowing. So Bob generates 2 prime numbers. I'm choosing a couple of smaller prime numbers here because I'm going to ask you guys to do some of these by hand in a moment. So when I ask you guys to do this on the final exam, because it's going to show up on the final exam, I am going to choose smaller prime numbers, because if I choose really big ones, it's going to take you forever. So Bob generates 2 prime numbers, let's say 19 and 23, which he keeps as his secret key. Note that this means that, note that 19 times 23 is equal to 437. So that's what n is going to be. He also chooses 61 as his exponent, and he publishes 437 and 61 as his public key. Okay, so that he tells to the world. He's like, hey everyone, if you want to send me messages at n, the modulus n is equal to 437, and the exponent 61. Okay, so then Alice is like, oh, I have a message. I want to send a message 196. So she takes 196 to the 61st power. Oh, I just dropped my pen. To the 61st power, so then you get mod 437. That turns out to be congruent to 9. So the message she sends is just 9. He's like, hey Bob, my message, encrypted message is 9. I sent it to your public key, so you know how to decrypt it. Well, Bob can decrypt because he knows the factorization of 437, so he knows what phi is. So he knows that phi of 437 is 396. On the other hand, Eve cannot decrypt the message unless she's able to factor 437. So now for a small enough number like this, Eve probably would be able to factor it. But you picked a really big set of primes, a really big pair of primes, Eve probably wouldn't be able to factor it, and then wouldn't be able to solve this. Let's go through the decryption stuff in detail. So Eve intercepts an encrypted message, 9, sent to a public key, 43761. Being really, really clever, Eve does actually factor this. Eve is like, oh, hey, I know that 437 is equal to 619 times 23. And so now Eve has broken the key and knows what the secret is. So once Eve knows what the secret is, she can actually compute the answer. So what does she need to do? Well, then she just needs to decrypt it the same way Bob would. So she needs to compute the 61st root of 9 mod 437. Well, how do we do this? Well, we know that phi of 437 is equal to 18 times 22, which is equal to 396. So 396 is equal to 61 times 6 plus 30. 61 is equal to 30 times 2 plus 1. 30 is equal to 30 times 1. And so therefore 1 is equal to 61 minus 30 times 2. 1 is equal to 61 minus 396 minus 61 times 6 times 2. So 1 is equal to 61 times 13 minus 396 times 2. And the m that we have here is 13. So what we get is that 9 to the 61 first root of 9 is congruent to 9 to the 13 mod 437. Oh, well, now we know how to compute that. You just have to look at expand these powers. 9 to the 1 is congruent to 9. 9 squared is congruent to 81. 9 to the 4th is congruent to 6. You can multiply that out and check that. And then 9 to the 8th is congruent to 36. So this is congruent to 9 to the 8th times 9 to the 4 times 9 to the 1, which is congruent to 36 times 6 times 9, which is congruent to 196. Okay, so then Eve knows what the final answer is because she could break it by factoring. Okay, you all now know RSA encryption. You all can actually send secure messages to each other now. So let's do it. Let's try it out. Encrypt the message 7 using the RSA public key nk is equal to 7713 without factoring 77. So of course, actually it doesn't really matter if you factor it, but try to do it without. And if you need a reminder of the algorithm, it is on your handout, as well as the slides for today. So it's on the handout that I gave out last Wednesday. Okay, looks like we've started getting a couple answers. Oh, we have 3 different, oh no, just 2 different answers. Hopefully I did it right. Whenever people start answering lots of answers that weren't the answer I got, I'm always really concerned that I made a really silly arithmetic error somewhere, which is quite possible because I make arithmetic errors as well. But so we'll give it another moment and see what people equalize out to. Okay, so hopefully everyone at this point has figured out that in order to figure this out, all you have to do is you just have to take 9 to the 13 mod 77. So that's all you have to do in order to compute this. So let's work through that carefully by hand. So what's 9 to the 1? 9 to the 1 is just 9. 9 squared is 81. But 81 is, of course, congruent to 4. 9 to the 4 is 16. And 9 to the 8 is 256, which is congruent to 25, I think. So let's see, 77 times 3 is 21, 21, 231. So yeah, so that's 25. So that means that this is congruent to 9 to the 8 times 9 to the 4 times 9, which is, of course, 25 times 16 times 9. Well, when you multiply these together, that's 400, right? Because, yeah, that's 400 times 9. Well, 400 divided by 77. Well, 77 times 5 is 35, 35. So that's 385. So that's congruent to 15 times 9, which is congruent to 135. And 135 minus 77 is going to be, well, it's 15, that's 8. So let's take away one of those. So that's 1, so that's 12, that's 5. So this is congruent to 58 mod 77. And of course, in order to do that, the reason we were able, one other thing you want to be careful about when you're encrypting messages is you do want to check that the GCD of 9 and 77 is equal to 1, and that the GCD of 13 and 60 is equal to 1. If you don't have those, then you can still encrypt, but you might not necessarily be able to decrypt. So those are still things you should check, because like we've said, you really should be checking your conditions whenever you're doing stuff. But yeah, so the answer here is C, 58. And it was relatively straightforward. It was just taking a modulative power. So that's all the encryption was. But now, what about decryption? So decryption is going to be, is also pretty tricky. So let's decrypt the message, encrypt it. So this is a different message, but I'm going to use the same RSA public key, 7 and 13. 77 and 13, with 77, the secret key 77 is equal to 7 times 11. The encrypted message is 26, and we want to decrypt this message. As a helpful hint, I've already given you the combination for 1, so you don't have to do the Euclidean algorithm. So 1 is equal to 60 times 5 minus 23 times 13. So now, what's the decryption of this message? And let me zero out the chat. So this is going to take a little bit longer, I think, for many people. But let's just start by what are we trying to do? So we know a to the 13 is congruent to 26 mod 77, right? Because that's what you're encrypting some message A that's going to be congruent to 26. So there are a couple ways you could do this. One way you could do this is, well, you could just check each of these answers and see if they're correct. That's not the way we want you to do it, because you're on the final exam, it won't be multiple choice. But instead what you can do is, well, that means that A is congruent to the 13th root of 26 mod 77. And we know phi of 77 is equal to 6 times 10, which is equal to 60, because we know the prime factorization. We can check that the GCD of 26 and 77 is equal to 1, and the GCD of 13 and 60 is equal to 1. And because I gave you this combination, which I won't be doing on the final exam, so make sure you can do that. But since I gave it to you in this case, that means that the 13th root of 26 is congruent to the 13th root of 26 to the minus 23 times 13, which is congruent to 26 to the minus 23, which is congruent to 26 to the 37. Now, this is a little bit painful to do because you need to find the 37th power, but we can do that. So 26 to 1 is congruent to 26. 26 squared is congruent to 676, which is congruent to 676 minus 616, which is congruent to 60, which is congruent to minus 17, and so on. So I'm not going to write them all out, but the punchline is at the end of the day, you get 26 to the 37 is congruent to 5, which is the answer there. And hopefully I did that right. If I didn't do it right, well, please check me in your own time after class. And actually work through it, because I will be expecting you to be able to take these powers, and there is some chance I did it wrong. But let me finish out the lecture. So in summary, basically we have hybrid crypto systems, and it's because, and one of the other things you might have noticed is that public-private key encryption seems to be a lot more work than the symmetric encryption we did on Wednesday, right? So last Wednesday, we did these symmetric encryptions, and you were able to encrypt entire messages in like a short amount of time because you're just adding or subtracting, right? And there are more complicated symmetric ciphers, but in general, public-private key encryption is a lot harder because you have to do lots and lots of math. And this is even true for computers, which can do both, but they're much slower at public key encryption than they are at private at symmetric key encryption. And so in practice, and this is what we'll be doing this Wednesday in their interactive activity, Alice and Bob will use RSA to send a very short message, so maybe just a single number containing a key for symmetric encryption. So this way, basically, Alice is saying to Bob, hey, Bob, I know that you gave this public key, but it's really hard to do all this math to just talk to you. And so instead, I'm going to send you, I'm going to do all this math and send you a single message, which is a key for some other cipher. And then let's use this other cipher whenever we're actually talking to each other, because it's going to be a lot faster. And that's what we're going to do on this coming Wednesday. And with that, I will go ahead and end class. A couple reminders. The first one is that you have your quizzes this week. Hopefully you all already know that. The second one is that the student evaluations are now up. So if you want to tell me all the things I do right or wrong, please do. I do read all of my feedback, and it is very helpful in designing these sorts of courses for future generations of students. I know it's too late for you all now, but I very much appreciate it if you could actually give feedback. Having said that, thank you all very much, and I will see you on Wednesday.